Hi, everyone. Welcome to today's lecture. My name is Meltem, and I'm a research staff member at IBM Quantum. And today we're going to be talking about quantum machine learning and its applications on our path to quantum utility. Our goal will be to provide an overview of quantum machine learning applications that can be implemented on current and near-term quantum computers. Before we get started with the details, I would like to quickly mention what we will be covering in today's lecture. First, we will recap some preliminaries from machine learning. Specifically, we will revisit some concepts from classical machine learning. And second, we will talk about our first quantum machine learning model, which is a quantum classifier consisting of a variational circuit. Here, we will also discuss some strategies to encode data onto quantum computers. And later part of the lecture will focus on two different quantum machine learning algorithms for near-term quantum computers. The first one of these methods is quantum support vector machines, which utilize the idea of so-called quantum kernels. And the last method we will cover today is the quantum neural networks. With this overview, we are now ready to revisit some basic concepts emerging from classical machine learning. So the first question is, what is machine learning? As a simple definition, machine learning is a collection of algorithms that analyze and draw inferences from patterns and relationships in data. This way, these algorithms learn to perform specific tasks without being explicitly told how to do it. Machine learning algorithms use statistical techniques to improve performance on a specific task over time and to generalize their performance to unseen data. And machine learning algorithms are used in a very wide variety of applications. These applications range from image recognition to natural language processing and recommendation systems to areas like medical diagnosis, finance, and autonomous vehicles. And with all its applications, machine learning truly revolutionized the technology industry and how we as humans interact with it. Now that we've broadly defined what machine learning is, we can look at what it means mathematically. From a mathematical perspective, machine learning can be thought of as a function approximation and optimization problem. In essence, what these algorithms try to do is to approximate a true function g, that we call here, with a function that we here refer to as f. The true function g takes in some parameters x, which we refer to as data or input features. For instance, g could be a function that takes in pictures as inputs, and it outputs +1 if the image contains flowers, or -1 if it doesn't. And in this example, the pixel values of an image would be the data features that we feed into the function. Here we assume that g captures the true relationship between an image and its corresponding label, which tells us if it contains a flower or not. But in fact, it is almost impossible to define such a function that can take in as input and label all flower pictures in the world by explicitly defining the true patterns in a picture that constitute a flower. And therefore, we try to approximate it with another function f that we see here that takes in some subset of all possible data features. We denote the subset here as x hat. And most importantly, this function f also depends on some other parameters that we see here as the theta vector. These parameters are what the algorithm learns as it is exposed to training data. These are also referred to as weights that parameterize a space of functions, and the approximating function f is also called a hypothesis in literature. For instance, h here, that we see as an example, defines the hypothesis class that spans the space of third-degree polynomials for input x. So in summary, our primary goal when designing a good machine learning algorithm is to pick a good mathematical model or a hypothesis and to make sure that the theta parameters learn very well from training data, with the goal that in the end, we would like them to generalize well to be able to perform their task on data that they haven't seen before. There are also several different types of machine learning algorithms, as we see here. Broadly speaking, we can define three categories. The first one is called supervised learning, where the data that is used to train the model is labeled. In our previous example, we defined the task of identifying if an image contains a flower or not. In this example, the model would be trained with images both containing and lacking flowers, and these images would be associated with the correct labels that place them into one of the possible categories. This is therefore an example of supervised learning, since the training data is labeled. And more specifically, this is a classification task because the model outputs one of the possible discrete classes. If we have an algorithm that predicts values from a continuous interval instead of discrete classes, then we refer to this as a regression algorithm. The second type of machine learning algorithm is called unsupervised learning, where in contrast to the previous type, the training data here is not labeled. These algorithms usually try to find or group patterns and structures in datasets. Some algorithms in this class are dimensionality reduction and clustering algorithms. Also, some generative models, such as the generative adversarial networks and variational autoencoders, are also in this category. Unlike discriminative models, which learn to predict labels corresponding to input data, generative models aim to learn the underlying distribution of the data itself. And they do this in order to generate new data samples that exhibit similar characteristics to those in the training set. The third type of machine learning algorithm is called reinforcement learning, and this one is actually quite different from the first two categories. Here, the algorithm learns to make decisions by interacting with an environment. And in reinforcement learning, a so-called agent receives feedback in the form of rewards or penalties based on its actions. And the goal of the agent is to learn the optimal strategy to maximize the cumulative reward over time. And with this categorization in mind, we will mainly focus on algorithms and examples that are under the supervised learning setting in the following sections. We can now summarize the workflow of generic supervised learning models. First, we have our data set with labels, which will be used to train the model. We can denote this as a tuple containing the input features xtrain and their true labels y. Now the model takes in the input features xtrain and predicts a label, which is y hat. Recall that the goal of the model is to learn the optimal parameter values denoted theta here. For the first step, these values are often sampled from a random probability distribution, though there can be more sophisticated initialization strategies for machine learning tasks, for machine learning models to warm start the training. Now that the model made a prediction y hat, we need to define a loss function first, which is essentially a metric that tells the model how far away the prediction is from the true label. There are several different loss functions that we can define, and here we have an example of the mean squared error loss, where we compute the differences of the predictions for the training inputs from the true labels, square them, and then sum those up. This gives an overall score of how well the model is performing on the training data set. Note that the better the predictions, the lower the cost function is, and vice versa. Therefore, we use optimization techniques such as gradient descent to update our parameters theta in a direction that lowers this cost function. To do this, we can use methods like, as we see here, we can use method like gradient descent, which computes the gradients of the loss with respect to the model parameters and updates them in the direction that lowers the cost. After the parameter update, we repeat this whole procedure many times using the training data set at hand until the algorithm converges. A well-trained machine learning model will output a low-cost function on unseen data, which means data that it hasn't seen during training, and this is an indicator of how well the model generalized. So in summary, how well a model generalized is captured by the following plot that we have here. This picture refers to the so-called bias-variance trade-off phenomenon. And it means that if the model doesn't perform well on the training data, this means that we're in the underfitting regime. For instance, we may have chosen a hypothesis class that doesn't have enough parameters to capture all the complex patterns inside the training data set. And in this regime, the model has high bias and low variance. And on the contrary, if the model works very well on the training data set, but performs poorly on the unseen test data set, this could mean that the model overfit to training data and could not generalize enough to perform well on unseen data. And in this regime, the model has low bias but high variance. And ideally, our model should be in between these regions, working at optimal capacity. So this was our recap of some machine learning preliminaries that encompass general concepts shared across both classical and quantum machine learning. And in the following section, we build our first quantum machine learning model, and this will be a quantum classifier that we build using a variational circuit. Now we're ready to start exploring the quantum counterpart of machine learning. First, if you search for quantum machine learning on the internet, you will most likely encounter this picture that we have on the left. This picture summarizes the types of data sets and processing devices that we can consider in machine learning and their combinations. For instance, CC here means that we have a classical data set at hand, such as images, sounds, or text that we can store on classical computers, and that we also use a classical computer to run a machine learning algorithm on this classical data set. This is precisely the classical machine learning setting that we discussed in the previous section. And if we take a look at QQ, for instance, now this means that we are using a quantum computer to process quantum data. And quantum data could be thought of, for instance, a set of measurement outcomes obtained from a quantum device, or this could be some state that has been prepared on a quantum computer by another algorithm in the first place, and we can do machine learning on the same quantum computer. However, when people talk about quantum machine learning, they usually refer to this CQ regime that we see here, where the data set is classical and the processing device executing the machine learning algorithm is quantum. For the supervised learning setting that we have on the right, this would mean that the model execution step, shown in a box here, would be executed on a quantum computer. This also means that we need efficient ways of uploading classical data sets onto quantum computers for these algorithms to work well. Another remark is that there are, broadly speaking, two different types of quantum machine learning algorithms, which are near-term and fault-tolerant. And for fault-tolerant algorithms, they require error correction on quantum computers and therefore are beyond the capabilities of near-term hardware. Some examples in this area include the HHL algorithm for solving a system of linear equations and the principal component analysis. On the other hand, near-term quantum machine learning algorithms can be implemented on near-term devices, which have a limited number of qubits with shorter coherence times, and they perform noisy operations. These practical applications include quantum support vector machines and quantum neural networks, and on our path to quantum utility, these are the algorithms that we will explore in the second half of our lecture. Here is now the workflow of our first quantum classifier. We have the same outline that we set for the supervised learning setting. First, we have a classical data set that we train the model with, and we need to have efficient ways of encoding the data set to our quantum computer, because now the model, which is mathematically our approximation function f, or our hypothesis, this will be computed on a quantum computer. And this will result preparing some state psi on the quantum hardware itself. And next, we need to define a quantum circuit that also relies on some parameters theta, similar to the classical setting. As the model trains, the parameters in our quantum circuits will update by learning from the training data. As you can see in this picture, defining a parameterized quantum circuit simply means inserting some unitary gates into our quantum circuit that depend on a set of parameters. Note that in literature, such parameterized quantum circuits are also referred to as variational circuits or an ansatz. So these terms are practically used interchangeably. Finally, we make measurements on the quantum hardware to either get a probability distribution over possible outcomes or to estimate the expectation value of an observable. We can now classically post-process these outcomes to decide what our model predicted, for instance, which class label is predicted for a given input from the dataset. Here is the task that we consider in this section. The goal is to do a binary classification, meaning we would like the model to learn and predict which of the two classes a certain data point belongs to, and we label these two classes as +1 and -1. In summary, first we encode the classical data into a quantum state and then apply a parameterized model. Finally, we measure the circuit to extract labels, which are fed into the cost function that the classical optimizer uses to update the model parameters until it converges. Now we will take a look at some standard methods of uploading classical data to quantum computers. This first method that we have here is called basis encoding, and as the name suggests, in this method, different data points are encoded as different computational basis states of the qubits. As a specific example, consider the 2x2 image that we have above and assume that it has the corresponding pixel values associated with it. First, we construct the feature vector using these pixel values. We then convert these features to binary representation. In this representation, every bit is associated with one qubit that is prepared in the same computational state. So to prepare the one basis state, we can simply flip the qubit state with the next gate. So in this example that we see here, we would need 8 qubits to encode our classical data. The second data encoding method that we can employ is called amplitude encoding. And here we encode the data directly into the amplitudes of the quantum state vector itself. This encoding strategy is more dense than the previous one because n qubits live in 2 to the n dimensional Hilbert space, and therefore we can encode data futures using only a logarithmic number of qubits. In our example with 4 futures, as you can see, we only need 2 qubits for this encoding method. But the downside of this method is that the circuit that prepares the state, this unitary U alpha that we see here, can get quite deep for general states that we want to encode. Looking at our specific example, to encode our futures as amplitudes, we first need to normalize the future vector since wave functions themselves are normalized. Then we can use software functions like Qiskit's built-in state preparation function class to synthesize the encoding unitary U that we see here. A third method that we can use for data encoding is called angle encoding. And here we encode the futures directly into the angles of the parametric gates. For instance, by assigning each future 1 qubit, we can construct this following circuit that we see here. Here we choose to encode the futures into the angles of the X rotation gates. So each qubit is initialized to one of the superposition states seen below. So the overall state after angle encoding is the tensor product state that we see in the first equation. There's also a variant of this method called dense angle encoding. This version encodes 2 futures in a single qubit by placing the second feature into the relative phase of the qubit, as we see in the second equation. And therefore, dense angle encoding requires half the qubits that the regular angle encoding requires. Now we introduce a more sophisticated data encoding strategy referred to as higher order encoding. We also call this a future map, and we will actually revisit this concept more in depth as we discuss quantum kernel-based methods in the next section. For now, as a data encoding method, the reason why we call this higher order encoding is that instead of only loading the futures into the rotation gate angles like in angle encoding, we also encode a higher order function of the data futures into the rotation gates. Here in this example, you can see that we start off with Hadamard gates, bringing the qubits to superposition, followed by Z rotation gates. Then we create entanglement between the qubits with the 2-qubit C0 gate. Finally, we add a rotation gate, whose rotation angle is the product of the 2 input features. Due to this product, we effectively encode higher orders of our data. We can also repeat this data encoding block in the circuit, increasing the depth of the future map. And the reason for this will become more clear in the next section. In addition, this particular future map that we have here is called the ZZ future map and has been implemented in Qiskit as a function if you would like to take a closer look. Here we summarize the different data encoding methods that we discussed so far. The main takeaway from this slide is that different data encoding strategies require different resources in terms of number of qubits and the circuit depth or the state preparation runtime that they require. This trade-off is especially apparent if you take a look at this table in amplitude encoding, as it results in the least number of qubits among all methods listed here, but in turn it suffers in runtime or circuit depth. So now going back to our quantum classifier, so far we talked about different ways of constructing the UX in our variational variational model. Now the second step is to construct and synthesize a good ansatz W that will eventually learn to do the classification task after having updated its theta parameters. And designing a good ansatz for a specific problem is actually a very active research area and quite often might not have a very straightforward answer. One of the reasons for this is that we need to design variational circuits in a way that is both expressive and is hardware efficient. An expressive ansatz effectively means that it contains enough degrees of freedom such that it can reach the part of the optimal solution space with its tunable parameters. While constructing such circuits, we're also constrained by the circuit depth we can have before noise fully accumulates or the topology, when we also need to consider the topology of the hardware. For instance, having too many 2-qubit gates that are far away from each other results in an overhead of swap gates. when we transpile the circuits and is therefore not desirable. A good ansatz in practice should therefore balance expressivity and hardware efficiency. In this particular example, for instance, the ansatz consists of single qubit rotation gates with tunable parameters and 2 qubit CNOT gates which are laid out in a linear nearest neighbor fashion to create entanglement. I also referenced the paper below if you would like to learn more about hardware efficient ansatz in the context of quantum machine learning. Okay, so now that we have our variational circuit, we need to make measurements to extract the information from the model for classification. The labels that the model predicts will be later used to compute the loss function, and eventually a classical optimizer will make updates to the parameters to minimize the cost. For our binary classification task, there are 2 simple ways we can use to make a binary decision on the labels. In the first one, we sample the probability distribution over all possible bit strings and can use the parity function later to make a binary decision from the sample distribution. If, for instance, the probability of observing even parity is greater than the probability of observing odd parity, then the model outputs the +1 label, and if not, then it can output the -1 label. So in Qiskit, we can obtain the probability distribution using the sampler primitive. Another option is to discard all qubits except for one, and to measure the expectation value of, for instance, the poly-z observable on that qubit. And since this value is in the -1 +1 interval, we can use 0 as the cutoff value and label outputs +1 if the expectation is greater than 0 and vice versa. And in Qiskit, we can get the expectation value using the estimator primitive. And after extracting labels, we use a classical optimizer to lower the cost function. There are several different types of optimizers that one can choose from, and broadly speaking, we can categorize them as gradient-free or gradient-based optimizers. In the case that we use an optimizer which is gradient-based, then we need a way to compute the partial derivatives of the model output with respect to the individual parameters that we will update in the circuit. And we can do this by using the so-called parameter shift rule. What the paper referenced below has shown is that the gradient with respect to a parameter can be computed by measuring 2 circuits. First, we shift the parameter by an amount of pi/2 and compute the output. And then we repeat this shift in a value of -pi/2 in the opposite direction. And the difference of these 2 circuit estimations divided by a factor of 2 is the gradient with respect to that particular parameter. And we actually need to repeat this for all parameters in our model. As a remark, there is also an optimizer called SPSA that is quite often favored in practice on quantum computers due to its lower computational cost and is known to perform well under noise. This method has its own way of approximating the gradients, which is less costly than the parameter shift rule that we have here. Therefore, I would also encourage you to explore SPSA for your own quantum machine learning tasks on near-term quantum computers. Up until this point, we discussed the ingredients of a variational quantum classifier, and in this new section, we will introduce the idea of quantum kernels and the quantum support vector machines, which are based on quantum kernels. We first begin by revisiting the concept of support vector machines from a classical machine learning point of view. So again, let's assume that we have a binary classification task where we're trying to place the training data into 2 classes of labels. And this time, let's take a look at this 2-dimensional data that we see on the left side of the plot. And one thing that we can do, for instance, when we're taking a look at this data, is to try and find a line or a linear decision boundary that separates these 2 classes. And so, or in general, because we're in 2-dimensional space right now, the word that I used is line, but if the data lives in higher dimensional space, in general, what we're looking for in this setting is a separating hyperplane. And how can we do this? So going back to this 2-dimensional example, we're trying to find a line, right? But there are, if you take a look, infinitely many lines that can separate the 2 classes of data that we have here. So if we tilt this line a little bit in that direction, that is still a separating hyperplane or a line that correctly separates these data points into their corresponding labels. But a particularly good way of thinking about this is to try to come up with the line so that when it separates the two classes, it has the maximal distance from itself to the data points that are nearest to the decision boundary itself. So this is in literature called the margin. And what we're trying to do in this support vector algorithm is to try to find the line that has the greatest margin to the nearest points that have the nearest distance to the separating line itself. And these nearest points, after we run the algorithm, are called support vectors. That's where the algorithm gets its name from. So if we take a look at what we call the primal formulation in this setting, again, because we're looking for a linear decision boundary, our hypothesis or the model that we're trying to learn has this form that we see here, which is a linear equation. So in this model here, the goal would be to learn the theta parameters, and the function itself has this inner product form plus some bias. And if we do a little bit of mathematical formulation, mathematical manipulation to come up with another formulation of the same problem setting, we end up with the so-called dual formulation. And as you can see here, the dual formulation this time includes the training labels xi and yi. So xi are the data points that we see on the left, and yi's are the correct labels that correspond to the data points in the training set. So we slightly reformulated to the dual version of the equation, and it actually looks a little bit more complicated than the primal formulation itself. But the reason why we switched to this particular way of this support vector machine equation will become a little bit more clear when we move on to the next slide. And the slight difference between the primal and the dual formulation is also the parameters that we're learning out of the algorithm. So in the primal formulation, our goal was to learn the correct theta parameters, but in the dual formulation that we have here, the model will learn the alpha parameters after it learns from the training data. Okay, so the idea of support vector machines is very well motivated in this particular slide, and that case is actually when data is not linearly separable. So if we take a look at this picture on the left, we see two classes of two-dimensional data, and it has input features x1 and x2, which are laid onto the two axes that we see on this plot. Again, our goal was to find a linear line that's a linear hyperplane, or a line that separates these two classes. But as you can see very clearly, there is no such line that can do that if we only constrain ourselves to the features that this data set currently has. But one trick that we can do is that if you take a look at the right side of this slide, we can also increase the number of features that we have in our feature map. And we can define the product of the two initial features, x1 and x2, and add that to our original feature map. Here we can see that now we moved on to the three-dimensional space, but we can immediately find a separating hyperplane that separates the two classes that we have in our data set. So this should motivate why moving on to higher dimensional spaces can result in us being able to find linear decision boundaries that we're not able to find when we are in the original lower dimensional feature space. Okay, now that we know that using a feature map to get to higher dimensional space can allow us to successfully find a separating hyperplane, we can replace the original feature vector x that we have in this equations with the feature map vectors. So this simply means initially, we had our original feature map. In this example, it was x1 and x2. And then we replace it in the both formulations with this phi of x, which is the feature map. Now these vectors include x1, x2, and their multiplication, if we specifically constrain ourselves to the previous example. And if we take a look at, so we know that this is beneficial, and if we take a look at why we switched to the dual formulation in the first place, the answer lies here in the second column of equations. So if we stick ourselves to the primal formulation, solving this requires us to explicitly build inner products between the feature map and the theta parameters that we're optimizing over. But in fact, this feature map vector can be very high dimensional, and in fact it should be, because we just saw the idea that we can find a separating hyperplane if we move on to higher dimensional spaces. But if we take a closer look at the dual formulation, these explicit inner products between the optimizable parameters and the feature space is now replaced by inner products that only rely on inner products between the feature maps themselves. So there are computational cases where we are able to compute this value, this inner product between the feature map vectors, without ever explicitly building the feature map, without ever explicitly computing the feature map itself. This is what's referred to as the kernel trick in the literature. And in fact, these feature maps can be infinite dimensional. So it's not computationally feasible to compute uncountably many features of an infinite dimensional feature map. But we might still be able to compute these inner products. And as you can see, these feature vectors take in different values from the data set. And all we need to do is to plug in different combinations of data values into this inner product, and we need to come up with an efficient way of computing the kernel without ever explicitly building the high-dimensional feature vector. So this was the idea of a classical kernel. Now we are ready to discuss why we would why we would want to do this on a quantum computer and switch to a quantum counterpart of the kernel definition. So quantum computers, or quantum states in general, allow for a very natural definition of a quantum kernel. And if you recall the higher order encoding method that we discussed when building a quantum classifier, a way of thinking about it is also simply to interpret the encoding of an input x into a high-dimensional quantum state phi x as a feature map. As we will see on the next slide, we can use a quantum computer to estimate a kernel. We can then run the support vector machine optimization classically on the quantum kernel itself. The important question is, when can we expect to gain an advantage from computing the kernel on a quantum computer? The answer is not so simple, but what we know is definitely a necessary but not a sufficient condition is that quantum kernels can only be expected to do better than classical kernels if they are hard to estimate classically. So this needs to be satisfied for us to be able to expect an advantage by computing the kernel on a quantum computer instead of a classical one. Otherwise, we can simply estimate the kernel classically, and we can't expect to gain any more advantage from doing this on a quantum computer. It was actually shown that learning problems do exist for which learners with access to quantum kernel methods have a quantum advantage over all classical learners. So we do know of some data sets that have a specific type of a group structure that can definitely benefit from having access to a quantum kernel. To read more about this technical results, I would encourage you to check out this paper that I have listed here, Covariant Quantum Kernels for Data with Group Structure. And this is one example of where we can expect a quantum advantage using a quantum kernel. So after having defined the quantum kernel, we can now define the quantum support vector machine algorithm. So first, the part of the support vector machine algorithm that moves onto the quantum computer is the kernel computation itself. So first, we define the circuit, which is the quantum kernel estimator. So if you recall, this kernel is an inner product between the feature maps that take in different data features as inputs. So they're indexed differently, xj and xi. We can even think of this as a matrix that are with values indexed as kijs. So we need to compute these values efficiently. So if you take another look at this expression that we would like to compute out of a quantum computer, you can also see that if we start in the 0 state, and if we prepare the state that we see on this picture here, this also corresponds to measuring an all 0-bit string out of a quantum computer. So this expression that we would like to compute translates to the probability of obtaining an all 0-bit string out of a quantum computer if we were to prepare the state. And how do we do that? We define our feature map and let it be a unitary that takes in xi, one of the data points. And then we implement the adjoint of this feature map unitary, and then let it take in the value of xj. And that's the state preparation circuit for our quantum kernel estimator. And then we make measurements. So how does the full algorithm work? For ij in the training set, what we do is we prepare this state, and let, as I mentioned earlier, let kij be the probability of measuring an all 0-bit string. And then after we obtain the Kij values, we plug them simply into the dual form. The rest of the computation is handled classically. And we can solve this similar to what I had mentioned previously using quadratic programming software or some other optimization software that is tailored towards solving SVMs. And then what this algorithm does is to return this alpha I values because we're in the dual form. And now we can use the learned parameter values alpha i's to make a decision on the labels that the new unseen input features. We're now at the last section of our lecture where we will explore quantum neural networks as an application of near-term quantum machine learning. First, we begin by reminding ourselves the concept of classical feed-forward neural networks. A neural network is a computational model which is loosely inspired by the structure and the function of neurons in a brain. These neurons, which are nodes as we see them here in this picture, are organized into layers and are connected through weights. They process signals that they receive from a previous layer and transmit them to the next one through connections. And if we focus on one of these neurons, we have the building block of a neural network, which is called a perceptron. And mathematically speaking, a perceptron takes in an input vector x and computes its inner product with a trainable weight vector plus some bias. And very importantly, this perceptron applies a nonlinear activation function on top of this computation. These nonlinear activation functions are responsible for the great expressive power of neural networks. And another way to think about it is that, as we see here, these inner products, and if we stack them together in this neural network picture here, they are linear matrix multiplications. And suppose that if we didn't have these nonlinear activation function in between each layer applied by the neurons themselves, then we would be able to apply one linear function after another, one matrix multiplication after another, and this whole giant model that we have here would be a very big matrix multiplication itself. So this would simply be a linear model that wouldn't be able to capture the complex patterns that deep neural networks can. The deep neural networks, I really want to emphasize, owe their great expressivity to these nonlinear activation functions that they have in between layers. Therefore, they are fundamental in neural networks. So the next thing that we're going to be discussing in this regard, when we're making an attempt to build a quantum perceptron, is to introduce this nonlinearity into our quantum circuits. This is because without additional considerations, quantum circuits are only circuits that can implement unitary operations. And unitary operations are simply linear operations, right? So we need to think of additional ways that can implement nonlinearity if we would like to find the quantum counterpart of a perceptron or a neural network that has this expressivity to be able to approximate a function like this true function g, which has which can detect complex patterns. And there are several different ways that one can introduce nonlinearity to a quantum circuit. There have been several different attempts in this regard, but several sources of nonlinearity can be thought of, for instance, by making measurements. Measurements are nonlinear operations that we can perform on a quantum circuit. And even if we do these, for instance, in between circuits with a technique called mid-circuit measurements or dynamic circuits, and continue with the quantum operation with a quantum gate after having made measurements in the circuit, this would be a source of non-linearity in our quantum circuit. There is also one of the most initial papers that proposed the quantum counterpart of a perceptron was utilizing this quantum Fourier transform based method. And this paper also discusses how we can introduce nonlinearity in our circuits. Again, there are several different ways, but these are examples of how we can introduce nonlinearity to our quantum circuits. So we can now look at one way of constructing the quantum part of a neural network. In this model here, so on the left, we again have the classical neural network setting, and the information flow that we have in these two settings is slightly different from each other. So in the classical setting that we see here, and this is a classical feed-forward neural network, information flow when we start with the input and would like the model to output a label for us, for instance, follows from left to right. So input goes in, as compute goes through one layer. There are connections that take the signal from the first layer to the second one and so forth. As I mentioned, there are nonlinear activations in between, but the information flow in this particular structure is following from left to right when we ask the model to give us a label or an output. The only time when the information flow is actually in the reverse direction is when this backpropagation is happening, and that is when we're training our model. We compute gradients with respect to the trainable parameters, weights, and biases. And the backpropagation algorithm now reverses the information flow, starts at the last layer, and makes sure that gradients are propagated through the network structure to update the trainable parameters. But it is when computing the output, the information flow follows from the input layer to the output layer, from left to right. In the quantum neural network setting, in this particular way that we can construct it, that has expressivity to resemble a classical neural network and has expressivity to approximate a true function g. In the general setting, consists of the following idea, and it uses the so-called data reuploading strategy. So what we do here, as opposed to the classical setting here, is that you see these blocks, different unitary blocks that are encoded in different colors. So this S of X here is the data encoding block, but it repeats itself within the circuit itself. So we first here load the data with this unitary. Then we have our ansatz within the structure with the trainable set of parameters, this theta 1 vector. As we progress through the circuit, we repeat the data encoding multiple times. So it's not just as the initial step as we see it here. And this data reuploading strategy actually has interesting theoretical implications. One paper that I listed here shows that with the help of multiple data reuploading steps, even a single qubit provides sufficient computational capabilities to construct a universal quantum classifier when assisted with a classical subroutine. So us being able to upload the data multiple times as we in the circuit gives us enhanced expressive power as a universal function approximator. And this allows the quantum neural network to approximate complex functions. So a specific type of quantum neural network that I would like to discuss next, because it is quite suitable for near-term hardware, is called a quantum convolutional neural network, which is inspired by a classical convolutional neural network. So I'd like to spend just a few minutes to go over this idea so that we can discuss its quantum counterpart. So a convolutional neural network consists of alternating layers, which are called convolutional layers, and pooling layers. So in a convolutional layer, we have matrices that slide over the input features, or if they're occurring in between the neural network itself, they slide over the signals that they received from a previous layer. And they mathematically perform convolutionals on this inputs that they're acting on, and they extract local information. So if this is, for instance, the first step, and if we have an image recognition task, we can feed the pixel values of an image, and our task will be to label whether, for instance, in this case, whether the image contains a Qiskit logo or not. So we take in the pixel values, put them together in layers, and a convolution matrix with trainable weights will slide over these pixel values to extract local information from it. What happens in a pooling layer is practically dimensionality reduction. We discard some of the information as we process with the help of pooling layers, and there are several different ways we can achieve this. For instance, we can use the maximum function, the averaging function, or the sum. And here, for instance, we would like to get from a 4x4 dimensional matrix to a 2x2 dimensional one. So we group them in these groups encoded in different colors here. And here we perform, for instance, the maximum function. So we get the value 3 here and discard all of the values that are less than that. this helps reduce the dimension of these networks. And in the end, usually there's a layer called fully connected layer with connections across all possible neurons, which then outputs a probability distribution over possible classes. And ideally, the class that labels that this picture has a Qiskit logo will have the greatest probability. And this is how a convolutional neural network works in principle in the classical machine learning sense. So the quantum counterpart of a classical convolutional neural network, the so-called quantum convolutional neural network, is in a sense inspired by a similar methodology, but there are quite a few differences. So I think it's good to use the word inspired here. So because we can't have sliding operations in the same sense that we have in a classical computation, but similarly, you can see we have unitaries that repeat themselves as if they're sliding across qubits. So these are, of course, fixed as they're placed as fixed gates onto the circuit itself. But you can see that the same unitary block repeats itself in a next neighbor topology in alternating layers. So this unitaries that constitute our convolutional layer ansatz are also repeated throughout the architecture. But the question is, like, how do we perform pooling in a quantum convolutional neural network? There are mainly two different ways that we can do this. Again, the goal, we have two goals. The pooling layer will reduce the dimensionality of the circuit, but also it'll be responsible for introducing nonlinearity into our neural network. As we discussed in the first slide, introducing nonlinearity is of great importance to be able to capture complex relations as we use these models as function approximators. So one way we can do is by employing something called mid-circuit measurement. So we can also have measurements in the middle of the circuit instead of, having them at the very end. What we do here is that we pair qubits, and for every pair of qubits, we make a measurement on one of the qubits at the pooling layer. And depending on the outcome, we apply the unitary V1. So this could be something like, if you measure 1 from this qubit, then apply the unitary V1. And if you measure 0, then don't do anything. It could be a decision like that. So this is the mid-circuit measurement version of doing pooling. The other way we can introduce nonlinearity in the circuit is by this tracing out operation. So it's a mathematical description for discarding qubits and not performing any operations on them. So what we would do is that we would let this qubit to sit and continue till the end of the circuit duration, but we wouldn't perform any other measurements on it. And mathematically speaking, this corresponds to an operation that we call tracing the qubits out, and it introduces nonlinearity in the system. So at each pooling layer, we discard half of the qubits, and we continue with a convolutional layer and another pooling layer. We can repeat this, however, as many times as desired for that particular application. And then occasionally, again, we have this block that we call the fully connected layer, but in a quantum setting, this is an entangling unitary that acts on the remaining number of qubits. And finally, we make a measurement on qubits and use these to make a decision on the labels decision on which label is predicted for the data that we provided in the first place. So convolutional neural networks, as I had mentioned, are particularly near-term friendly algorithms due to their main properties. The first is that QCNNs have a logarithmic number of layers and parameters with respect to the qubits that they start the circuit with. And this especially results in shorter depth circuits compared to some other algorithms that we have considered. And the second very desirable property that we will discuss in the next slide is that they don't suffer from this problem of so-called barren plateaus. And this becomes a very important issue in training quantum neural networks. And it is a great theoretical result that these circuit architectures don't suffer from this problem, making them very near-term quantum computing and quantum machine learning friendly architectures. So the last thing that I want to do in this lecture is to briefly summarize the issue of barren plateaus and to show that quantum convolutional neural networks, to emphasize that quantum convolutional neural networks don't suffer from it. So this issue of barren plateaus becomes a problem with randomly initialized deep circuits, and when we try to train them. And the phenomenon is that the gradients of the cost function vanish exponentially with the number of qubits under certain circumstances. So this especially becomes a problem if we have a circuit that has an ansatz structure similar to this, like an alternating layered ansatz. Things become quite hopeless if the circuit is quite deep, and especially if the cost function depends on if the cost function is global, meaning that the cost function is a function of almost the entirety of the qubits that we have in the circuit. For this type of ansatz, there is something that we can do. So if we constrain our circuits, our ansatz, to consist of shorter depth circuits, if we construct shallower circuits, and if we constrain our lost functions as we train this algorithm to be more local, to be rather local than global, then there is hope for mitigating such issues. And there are also, this is a very active research area, and there are also different initialization strategies that one can try to employ to avoid this issue of barren plateaus. And because of the structure that we took a look at for quantum convolutional neural networks, they inherently don't suffer from this problem. They discard qubits along the way, have logarithmic number of parameters and circuit depth, and their cost function is, because we discard qubits, the cost function becomes intuitively more local rather than global, relying on a less number of qubits. So they don't suffer, they have been theoretically shown to not suffer from this problem, making them great candidates for near-term quantum machine learning applications. So our goal in this lecture was to provide an overview of quantum machine learning algorithms that can be implemented on near-term quantum computers on our path to quantum utility. If you'd like to explore any of these concepts more in depth, I would also encourage you to revisit a previous Qiskit Global Summer School that took place in 2021, which focused exclusively on quantum machine learning. And I hope you find this information useful, and thank you very much for joining today's lecture.